All right, so let's start out with homonuclear, being same atom, diatomic molecular orbitals. So oxygen, diatomic oxygen would be an example. So how do we do this? Well, um, we look at the atomic orbitals that are available in oxygen, 1s, 2s, and 2p. Now, and we can populate those orbitals with electrons. We know that oxygen has 8 electrons. It's element number 8, so 2, 4, 6, 7, 8 in each of them. And we know that the 1s is going to be lower in energy than the 2s than the 2p. And then we're going to make bonding interactions. So ones that have similar energy and same symmetry, we can go ahead and make bonding and anti-bonding interactions. We can do that first with the 1s. So we can make a bonding interaction and an anti-bonding interaction. We can do that with the 2s, same type sort of thing. And then we can do that with the 2p, recognizing that the 2p, usually we define this as a z, but for our purposes, it doesn't matter too much right now, okay? For more advanced treatments, you do have to keep track of things a little bit better than we are going to, but for our purposes, it doesn't matter. But anyway, you can have 2p orbitals going head on, okay, in an anti-bonding way, or an anti-bonding way. And then the other ones are going to be the side-on, the pi bond type ones. So you can have ones like this. I've drawn these diagonally, but really what I'm trying to do is go in the board like that, okay? And so those would be the px and py, or y or x. Doesn't really matter. Those are arbitrary. Now, I've drawn it this way. Really, the 1s and the 1s, although they're same symmetry and similar energy, they're not really going to do this. It doesn't really matter for our for constructing an MO diagram if you do this, if you show a bonding and anti-bonding interaction, but they're not, because remember, these are core electrons, right? So they're really not involved in bonding. Really only the valence electrons are, which would be the ones in the 2s and the 2p. But anyway, we can go ahead and populate these. And so, we had 8 electrons on each of the oxygens, so we have 16 electrons here total, 2, 4, 6, 8, 10, 12, 14, 15, 16. Remember, we have to follow Hund's rule, which says that when you're in degenerate orbitals of the, degenerate means orbitals of the same symmetry, that then you have to first populate them in separate orbitals before you spin pair them. And the reason for that is pretty intuitive. It's because if you put 2 electrons in the same orbital, there's generally going to be more repulsion than if you put them in separate orbitals. So that's Hund's rule. We can label all of these symmetries of these, and I don't really want you to worry too much about this. This will make more sense, a little bit more sense, when we get into molecular symmetry and group theory in chapter 4. But I've shown them here just for completeness. But you can see, this has sigma G plus symmetry, this has sigma G plus symmetry. They have the same symmetry, so they can make constructive and destructive interference. Of course, they have the same symmetry. They're both 2s orbitals on an identical atomic element. But really, the main reason I showed these is just so we can keep track. I put the stars so we can keep track which ones are antibonding. Those are denoted by the asterisks, the stars, and the bonding don't have the stars. And so we can go in here and count, right, just like we did before. We have 2, 4, 6, 7, 8 bond. Sorry, I didn't count that wrong. Here, bonding 2, 4, 6, 7, 8, 9, 10 bonding electrons, and we have 2, 4, 6, 5, 6 anti-bonding electrons. So it's 10 bonding minus 6 anti-bonding. That's 4 divided by 2 gets you the double bond order of 2. So yeah, 2 molecular orbitals will mix if they are the same symmetry and similar energy. And so not only is that how you, let's go back to that, not only is that how you make molecular orbitals in the first place, is by mixing 2 atomic orbitals of same symmetry and similar energy, but it is the way you can get additional mixing of molecular orbitals that have same symmetry and similar energy. And so if you go back to our MO diagram, you'll notice here that there's a 2 sigma G plus. I got rid of the bottom 1s orbitals, okay? And 3 sigma G plus. Those have the same energy, same symmetry. The both sigma G plus symmetry. Okay, we'll get into what that means more in chapter 4. But for now, just notice that they have the same symmetry, okay? And there's not, they're pretty close to one another. But in oxygen, they're actually far enough away from one another that they're not going to mix, okay? And that's true for oxygen, fluorine, and neon. For boron, carbon, and nitrogen, the diatomics, these 3 sigma G plus and 2 sigma G plus molecular orbitals are close enough in energy for there to be significant mixing. And so what ends up happening in this case is that when you mix, it's sort of like making further making an anti-bonding interaction in a bonding interaction. So this one that was bonding becomes even more bonding, and it's going to go down in energy. And this one that was was higher in energy, was bonding, it becomes a little bit more anti-bonding, it goes higher in energy. And there's enough mixing here that there's actually a switching in the molecular ordering of the molecular orbitals. So you can see the 3 sigma G plus now is above the 1 pi U for diatomic boron, diatomic carbon, diatomic nitrogen. So in general chemistry, you may have learned this if you were taught molecular orbital theory at all. And I always found it very confusing because you don't talk about symmetry at all. And I never really knew where this came from until I learned about symmetry. And if you really want to learn more about this, we go a lot over sort of advanced symmetry concepts in my graduate level course, Chem 631. You can check out some of the videos on YouTube for those that I have for that course. But so that's cool. This is how the molecular orbitals mix, how I got these pictures. You basically just sort of walk your way through this. I'm just showing this for you for your kind of own edification. I don't expect you to know how to do this. But one thing I will point out is that, why is this, so the key is that for boron, carbon, and nitrogen, there's a switching of orderings because these 2 energy levels are small enough, small energy difference, significant mixing. For oxygen, fluorine, and neon, there's a large enough gap there that there's not a lot of mixing. So why is there a larger gap? So this is the correct energy order. There's no flip. Why is the gap larger for oxygen, fluorine, and neon? The answer lies into something we went over in the last video, which is the energy of the atomic orbitals. And we're talking about here, what are we talking about? We're talking about atomic molecular orbitals that came from 3 sigma G plus. So molecular orbital that came from the 2 P's and the 2 sigma G plus. Molecular orbital that came from the 2s. So what we really care about to determine the energies of this 2 sigma G plus and this 3 sigma G plus, we need to know something about the energies of the 2p atomic orbitals and the 2s atomic orbitals. How do we do that? We look at the ionization energies, right? And so if you look at the ionization energies, you'll notice that we said this thing about how the more core-like, the lower energy orbitals are affected by this trend more slowly. The slope here, the 1s was steeper than the 2s. And so what that means, if you look at the gap between the energies for like oxygen, let's do neon 2p and neon 2s is very large. But if you look at carbon 2p or boron 2p, right, and 2s, it's very small. And so that is where all this comes from. Okay, that's why you have more mixing for boron, carbon, and nitrogen. They're closer together in energy. MOs are closer together in energy because their AOs, their atomic orbitals, are closer together in energy from which they came. More mixing, enough mixing to switch the ordering of the molecular orbitals.